Okay, let's continue here. We're going to discuss input and output, both for user input and users seeing output, and also for inputting information from files. So I'm going to start in the console and just illustrate the input function in Python. So I'm going to create a result here, temp F, and I'm going to use input. And then in quotes, I'm going to put a prompt. Enter temperature in degrees F, colon space, like so. And then when I hit enter on that, it produces the prompt, and I can put in a number like 72. And we haven't done anything with it, but it is, if we take a look at the variable explorer, it's there. And one thing you'll notice is the result of the input function, as noted here, is a string or a text item. So our 72 is actually text. So if we want to do something with the result as a number, let me hit the up arrow to bring that statement back. And then let me put around it the float function, which converts a string to a number. And I'll put in 72 again. And now we'll see up here that it's denoted as a float or decimal type. And then I'll give an example of the use of a formula first. Temp C is equal to quantity temp F minus 32, that quantity divided by 1.8. That creates temp C, and it's shown up here as about 22.2. And then what we will do is we'll display that using the print function. Print temperature in degrees C is space, and then a comma, and temp C. And then you'll notice that it displays it. So that's a first example of the use of the print function along with the input function. And we'll come back to the print function later and get into more details. But now I'm going to go up to the editor, and let's just pop over to the slide for a moment to see what we've done here. And so your slide number 29 here illustrates just about what we accomplished on the console, and notes that the result is displayed in full precision, 15 to 16 significant digits. So that's what we've got there. Let's come back to the Spider editor and show something up in the editor field here, where I'm going to start by importing the NumPy module, and then I'm going to read in data from a text file that I have available, and you have it available too, year, comma, HURR. This is a file with hurricane data over the years. And I'm going to use the NP function, load text, TXT, and I'll put in the name of this file, which is Atlantic Hurricane history.csv. We get outside of that quote. Let me bring it down to the next line so it's easier to read. I'm going to use an argument unpacked equals true, which means the data on each record or line of the file is going to be separated into separate variables or arrays. And then I will say delimiter equals, and again, in quotes, I put a comma. And that is associated with a CSV file, which is a comma delimited file. And you could have another delimiter such as a tab character, but that's what we show there. Now, it is not liking something here. And it says perhaps I forgot a comma, and I did. So let's put that in. And now it seems to be happy. All right. So I can attempt to run this, and it found an error, and it's not finding my file. So let me come back up here on the upper right and get myself into the directory where that file is located, and we'll come over here and we'll try to run it again, and it still doesn't like it. So let me work on this a bit. Let us save this particular file, and let's go find the directory where the data file is located. I have to go through a couple steps here on my computer to find it. And I'll just call it file input test and hit enter. And then I will run it. And it seems to have run okay. If I look over here on the right in the Variable Explorer, I see the year is a long array that starts at 1851 and goes all the way up to a current year. And the hurricane is an array also of 167 items, which has the counts of the number of hurricanes. So let's pop back over to the slide and take a look at that. So what we notice here is up in the upper right, we have a text file where each record contains a year, a comma, and the number of hurricanes. Here I used a backslash file for line continuation. And while you're in the midst of a set of arguments in a function, you don't actually need that. You will recall that I didn't use it. Later on, you will need it if it's in like an arithmetic expression. This says we separate the items, and this is the delimiter. And it shows what we showed in our Variable Explorer, and it actually goes out to 2017. Down at the bottom, it shows the file where we obtained these data. And I will also say that there is a NumPy save text function to write data to a text file, and there are load and save functions to read and write binary files instead of text files. Okay, so let's go back now and take a look a little more closely at formatting. All right. So I'm going to start a new file up here using this, and let me get rid of the header. And I'm going to repeat the statements I had before. Temp F equals float input, and the string is enter a temperature in degrees F, colon space. So that's my first one. And then temp C is equal to, in parentheses, temp F minus 32 quantity divided by 1.8. And then we're going to be a little more careful in how we format our print statement. So we're going to print and then temperature in degrees C is, and then with braces, all right, curly braces, I'm going to put in a 0 colon, and I'll explain these codes later, 5.1 F, and then the end of that particular curly brace, come to the outside of that apostrophe, put a dot, and format temp C. Okay, so we'll take a look at the result we get here. So let us try to run this. It wants to know down here a temperature in degrees F, so let me put in 88, and the result is 31.1 in degrees C. So that shows a little more careful formatting of the output, and let's come to the slide to describe what that is a little more carefully here. And so the format string that we put into the text string here had several elements. The first is a 0, which means it's the first value to be formatted. And if we had a subsequent value, that next number would be 1, and so forth. 5 is the width of the field for the display, including the period for any decimal. 1 is the number of decimal places, and F means a floating point display. So, and then there is the format here, which is called a method that applies to the preceding string, and temp C is an argument to the format method, and this is the result that we get. And in addition to F for the formatting code, we have D for decimal integer, E for exponent, and G for a general format, which will either be an F or E according to rules that it follows, okay? So what we're going to do now is going to go back to the editor and we're going to illustrate some different examples of formatting for you, just so you can see how that looks. So let's come back here, and I'm just going to add in here, I'll say num days is equal to something like 45068, and then I'll use a print and number of days since 1/1/1900 colon, and then comes my format string with the braces, and it starts again with the 0 colon, and then 6D, a field of 6 and the decimal or integer format, and then I put a period and format num days. So we'll take a look at that, see what happens when we run that. And again, it's coming back and it's doing our temperature one again. So let's do that. And you can see the format shows 45068. And that number of days depends on where you are on the calendar right now. And that 45068 is not correct for today's date or the date when you are looking at this presentation, but it's pretty easy to find that number using the Excel spreadsheet if we needed to. So let us just comment out these first three statements here. Whoops, I need a number sign, not the percent sign from MATLAB. So we'll just do the hash or number sign there. And now it's left with this. And let's do another example. I'm going to put in Planck's constant, which is going to be 6.260, 7015 times e to the minus e34, which means times 10 to the minus 34. And just for the record, this is, the units here are joules. And then we're going to print. And I'm going to start this with a quotation mark. You'll see why. Planck's constant is, and then I will put in my braces 0, 15.8 E. Okay? And then I will add to that J times S for joule seconds. Or just joules, I guess. Joules. And then we will finish that and do our period and put format Planck, like so. Now, one thing, you can see the reason I used quotation marks here, because I wanted to use an apostrophe in the middle of the string. And if I had started this with an apostrophe, seeing this apostrophe, it would have thought that's the end of the string. So I used the quotation marks to allow me to put the string in as shown, okay? And then we can run this, and you can see how it provides us with that result, all right? And actually, I think it added one additional decimal fraction outside of what I had described here, which only had 7. So I could certainly change that to 7 if I wanted, all right? And then another thing that I can do at the end here is if I put a \n, all right, that says after doing this, go to a new line. So if I do this, it just adds a blank line, one more blank line under that, all right? Now, if I wanted to create a line separation from the previous line, I could do this \n at the beginning of that string and run that, and now it separates the two by a blank line. I could have also put the \n at the end of the one above, all right? So let's go on with a couple more examples. I will say mu is equal to 0.00005 of them, 1. And let me just put that the units here are meters, and it's the number of meters in a micron mu, all right? So let me come down and do a print statement. And I will say 1 micron is, and then I'm going to use a different format code here. And it's going to be 3.1 G, and then I will put in meters, and then my dot format, MU. So let us try that one. Let me get rid of this \n here. Let me try that one. And you can see that what it has done is the G has decided to use E format. All right. Now let's do another example. MM is equal to 0.001, again, meters, and I'll do print, whoops, sorry, and 1 millimeter is, and again, I will do 0:3.1 G, same format, all right, meters, come outside the parenthesis, format, MM, okay? So let's see what happens when we do that. Now you'll notice here, it decided that it could use just a standard decimal display instead of using the E display. So it decided it could use the F, and that is the nature of the G format. In other words, it will try to use F, but if it runs out of field width, it will move to using E. All right? So let's just pop back over to our slide now and show the examples, more or less, that we did, and show the results that we have there, and it shows what the G, E, and F are. Okay? So we'll continue, and we're going to move over and we're going to do some plotting now. Most of the rest of this segment of the workshop is going to be creating plots. Okay, so let us come back to our editor, and I will save this, and I will call it formatting examples, and then I can close this, and I'll open a new file that we can use for the plotting examples. And I just want to mention that based on the previous slide we looked at, that the appropriate units for Planck's constant is actually joule seconds, and that I had noted up here correctly on the slide and correctly here, not joules. Just want to make that minor correction for you. So that relates back to the file that I just had, all right, which was formatting examples. If I can find that here. And come back here and just correct that by putting joules times seconds here and joules times seconds here, and then save that and run it, and it shows the correct units. So I just want to keep things honest here, recognized a little mistake, and I corrected it. Okay, so let's come back over and consider plotting now, and I'm going to put in a couple of import statements which are typical. NumPy, when we're doing plotting, Matplotlib with its pyplot or pyplot submodule. And then we're going to start by creating a plot of an analytical function, introducing a couple new things here. So we're going to create an X array as np.linspace. This is very similar to what we can do in MATLAB. Go from 0 to 5, and we want 100 evenly spaced points between 0 and 5. Let me clean up the variable explorer here so we're not seeing everything we've worked with in the past. And now we're going to create Y, all right, using what we would call an array formula, np.cos, cosine of x times np dot hyperbolic cosine, cosh of x, all right? And then I'll subtract 1 from that. And the way that's working there is that it's allowing us to calculate this formula for each element in the X array and produce a set of Y results corresponding to the X values, okay? And then what we're going to do is do PLT plot X comma Y, and then we'll just leave it at that and try to run it. And let's look at our plots, and there's our simple plot. It shows a blue line, and it shows our range of X on the bottom and our range of Y results on the vertical axis. So there's a simple plot for you. And let's pop back to the slide to look at that. It points out the features that we've got here. If you do not put in the 100 here, it's a little different from MATLAB. The default value is going to be 50. And generally, if we're making plots, we just want enough points so that the resulting plot of an analytical function shows a nice curve. And this we can call a vectorized or array function, array formula, because this is not trying to do matrix multiplication or anything. It's just doing item by item for X. And here's our plot. We also show here a PLT show function, and sometimes that's required when you're running a Python script outside of Spider. Spider does not require it, okay? So let's come back now and let's see what we can do to improve our plot, all right? So the first thing I'm going to do is I am going to come into the plot command, and I'm going to put color equals, and in parentheses, in apostrophes K. K stands for black, and we'll look at the color codes in a moment. And then we will do plt.grid with empty parentheses. That's to add a grid to the plot. plt.xlabel. And let's have a label for the x-axis, and we'll call that simply x. plt.y label. And again, y. And then we can do plt, title. And we can put in a title such as plot of y equals cosine of x times cosh of x as our title, all right? And let's see, oh, I forgot, it's actually -1. Include that with the formula. And then we can run that, and we get a plot that is formatted a little bit better. If I wanted to take this plot elsewhere, like into a Word document or into a PowerPoint slide, I can right-click here, and I can do copy image. I can also save the plot in a file if I want, or I can remove it from the collection of plots. So that's just by right-clicking over there. So let's come back and look at our slide again. And you probably noticed, but in order to flip back and forth here on my computer, I'm just using an Alt-Tab combination. Hold down Alt and hit Tab. And so there's the code that I put in. Here are your color codes available. Now you can get into fancier color codes by using numeric specifications with what are called RGB codes, but I'm not getting into that here. And it shows a little bigger for you to see what the product of our plotting should be. And then we'll come back and we'll try something a little different. We'll come in and I'm going to abbreviate color by just using C equals. And then I'm going to add another one, LS, which is an abbreviation for line style. And in that, I'm going to put in a double dash for a dashed line. And then I'm going to put an LW for line width. And I'm going to put a numeric 2.5 there, all right? Just to show a little variation here. Let's see if this works. And it does. You can see we have a little thicker line, and now it's a dashed line. And once you recognize these abbreviations for color, line style, and line width, you'll want to use them because they're more compact and easier to enter. So let's look at the slide to see the details on that. And so here we've got C for color, LS for line style, LW for line width. And then just a single dash is solid. That's the default. Double dash and a colon for dotted, and a dash dot or a hyphen period for dash dot. So those are your standard line styles, okay? So this was doing an analytical plot. So if you want, you can save that. If I do a save as here, I think it'll take me back to my directory. And I could do something like plot analytical function and hit enter, and that saves that. And then I could get rid of that, and we could start a new example here and do a variation on plotting where we're not plotting a function, but now we're plotting data, all right? So let me, turns out I don't need NumPy here, but when I'm doing plots, I generally do need the pyplot submodule. Okay, now I'm going to put in some data for the freezing point of water or aqueous solutions of ethylene glycol, which is used as an antifreeze. So let's just put that in. I'm going to have a variable called PG. And here I'm not going to enter it as a NumPy array. I'm just going to enter it as a list with brackets. So I'm going to put in 0, 10, up to 60, and then skip 70, 20, 30, 40, 50, 60, 80, and 100. And these are just concentration of glycol by volume. And then we'll put in FP is equal to the corresponding freezing points, again, as a list. And that's going to be 0, which is what water is when we don't have any glycol. And then 3.4, actually greater. Not much of antifreeze there. And then minus 7.9. And then minus 13.7. And then we're getting down now, minus 23.5, I'm sorry. And so you're starting to see what concentration of solution is really going to get us a good freezing point depression. And then we will put in minus 36.8, getting down there, and minus 52.8. And there's going to be a problem there if we try to do that because you start getting slush. And then actually, as we continue, the freezing point depression decreases, and then we get minus 30. And then when we go to all glycol, we get minus 12.8. Sort of an interesting phenomenon there. And it doesn't like something here. No, it's okay with it. All right. So what we're going to do here is a scatter plot. So we'll do plt.scatter. And then we'll do pg, fp for our two lists. And then I'm going to specify a marker here for our scatter plot. And that's going to be an X, and then the color of the marker, C equals K for black, all right? And then grid, all right, and come down, and it's not liking something here, not PF, it's PG. Sorry about that. Should make it happy. And then we'll do, try to make it a little bit nice, X label, and we'll put in glycol percent by volume. And for Y label, we'll put in freezing point, DEGC, and we'll put in a title, fill it right here, freezing point of glycol, and I'll just say solutions here, like so. And let's see if we've got any problems or see what we get. And we do not have anything here, so we must have a problem. FP, PG. It says X and Y must be the same size, so we've got a problem here. So what do I have? 0, 10, 20, 30, 40, 50, 60, 80, 90, 100. I missed the 90, so let's put that in. Try it again, and there's our plot. So it shows our markers, and what you generally find for antifreeze solutions is that you're working with concentrations between 25 and 35%. You start getting into slushes down here that you don't want for an antifreeze liquid. Okay, so let's pop back over to our slide. And this shows the script, and then it shows your codes for markers, for a point, circle, plus sign, etc., all the way down to square, right? And we could have used NumPy arrays here, but scatter will plot numerical lists, so you don't need to have a NumPy array to do that. Okay, so let's come back and make some variations here. I'm going to change our marker here to S for square. And the color I'm going to use, I'll put R for red. And then I will put a separate argument, which will be edge color equals K. So now what I'm doing is I'm specifying the interior color of the marker and then the outline or edge color of the marker. Let's see what that looks like. So you can see now, if you look carefully, you can see the black outline around the red square. So that's some variation on that. And so I can save that particular, let me do a save as here. And I'll just call it plot glycol data markers. Okay. Now I'm going to go in and modify this, and instead of scatter, I'm going to change that to the plot function, all right? And then I'm going to start here with C equals K, and for the plot function, that means the lines plotted will be black. And then I'm going to do marker as square again, and I'm going to remove this. This is now for the plot function, and I'm going to have marker edge color, all right, as K, and then I'm going to add an argument down here, marker, sorry about that, marker face color equals white, all right? So this means that we're going to have lines, black lines, but then we're going to have markers where the data are. The markers are going to be black outline squares, white in the center, if we have done this correctly. So let's see what we get. And there we are, okay? So that might be a little more common for an engineering plot where you're connecting real data measurements with straight lines in order to better see patterns, all right? Now let's come back and look at a couple slides with that. Here is the slide showing our red squares, all right, still with the scatter function. And one of the reasons we're doing all these examples is so that you can go back either with the video or with the PowerPoint slides, and you can look at them to recall how you go about doing these things, all right? And then the second one, it looks like this, and I point out over here to the right that you can abbreviate marker edge color with MEC and and this should be a K, marker face color with a MFC. And that D there, I'll correct that later on for purposes of the PowerPoint slides that you see. Okay, so we're going to move on now. We're going to do some more complicated plots, and they are, the code is long enough that I'm not going to take the time to type in the code. Rather, I'm going to open the file with the code in it, and we're going to discuss the various statements in the script, and you can do the same, all right? So let's come back to our editor, and I'm going to save this one a little differently because I modified it. I'll just say plot markers and lines, okay, and save that. Then I can close that out. And I'm going to load a file called salt and mag chloride densities, all right? So let me go and find that if I can. Okay, so let's take a look at this, just saving a little time, not having to type all these things in. So we've got the density of salt solutions and mag chloride solutions at different concentrations. And concentration here is in weight percent. So if I wanted to make that clear in terms of my units, I could put a comment out here, weight percent, just to make that clear, all right? And then the density is in grams per cc. So if I wanted, I could put another comment here, G per cc or per cm cubed, however you want. And then you'll notice that we have two plot commands. Now this is going to plot the lines on the same plot. If you use MATLAB a fair amount, you may be familiar with the command hold on in order to make this happen, and in Python you don't need to do that. And so what we've got here is plotting the first set of data using the kind of arguments that we've already talked about, with the addition of an argument label equals NaCl, and the purpose of that is for a legend. And then we've got the second one here, and the marker is a square instead of an O. It's a dashed line, and the rest is the same, and the label is different. And then we've got our X label, Y label, title. There's nothing new there. But then at the end, we put in a command to plot the legend, all right? So let us run this guy, and we get a plot that looks like this. And you can see that we have two lines, and that the density of mag chloride as we go up in concentration is greater than the density of salt, all right? And you can see the legend that we have in the upper left here with the labels that we have. So if we pop back over to our slide, we can see that here where the plot is a little bit bigger, and you can see the various commands that we just described and the file that we used to load in order to see that. So that is what we have. And then we've got some other variations that we're going to apply here with a little more complicated script. So let's go back here and let's get rid of this one, and then let us open a file that's called salt mag chloride densities axes ticks. And the front end of this is very much the same, but then you'll notice that we've got our various arguments here. And this is pretty much the same. And then we get down and we have a statement with plot x lim 0 to 22. Now this forces the limits for the x-axis, and the y lim forces the limits for the y-axis instead of it determining them for us. And then we're going to place the ticks on the axis exactly where we want them, and that's why we need the NumPy module, because we use a NumPy function called arange, or arrange, but arrange with one R. And we'll show you the syntax of this on a slide in a moment, but for the X ticks, it basically says that we want to go from 0 to 24 in steps of 2. And you'd look at that and you'd say, now wait a minute, that 24 is one step beyond the 22 we spec'd up here. And it is because of the way that arrange works, in that it goes all the way to the end, except it only includes the step before the end specification, all right? That's a little tricky. So it goes 0, 2, 4, 6, 8, 10, etc., up to 22, but not to 24. And likewise, here we're going to 1.2, but we say to go to 1.22 in steps of 0.02, and it only goes to 1.2. The other thing we throw in here with the plot legend function is we determine the location for the legend, and instead of the upper left, we put in lower right. So as we do that, we get a result that looks like this. The legend is now down in the lower right, and we have some very neat formatted axes numbers exactly the way we wanted them to be presented. So we're taking a little more care now in how we present the plot. Let's go look at that. And so this duplicates the code in that particular file shown up to the upper right here. And down here, it gives you the syntax for the arrange. And let me make a note for a correction there. As I see it, the arrange has only one R, as you will note over here. So I'll correct that on the slide before I publish the slides. I've made a note of it. All right. So that is that. And now we're going to move on, and we're going to show you a little more when you have two series that you want to plot, but they have very different ranges, and you want to have a secondary axis on the right for one of the series. So let's come back to our editor and tuck this guy away. Click on that X, and let's open, and let's look for a file that's called twin axes. Down here somewhere. Here it is. Now, what we've got here is we're loading data from a file called furnace-data.txt. Now, this is not a CSV or comma delimited file. It happens to be a tab delimited file. And you can see here how we have denoted that with a \T for tab delimiter. And then over here, we've got unpack equals true again, as we had before. And this now gives us three items, T for time, fuel, and CO2. And so we have two series, fuel and CO2 versus time. They have very different magnitudes, so we want to plot them on the same plot with a left and a right scale. So we do the first one with a typical plot command, all right, for fuel. And then instead of doing just a plot command, we issue the twin X command to move the axis to the right side, and then we plot the CO2 data. So let's see what happens when we run that, and you can see what we get. And here, we could use a legend because of the different line styles as to which one is for the axis to the right and which one is for the axis to the left. And we'll deal with that in a moment. But that shows you how you can do twin axes. And again, as we jump back and forth, you can see what we have there in shifting the second one, the CO2 flue gas percentage, over to the right axis, and the normalized fuel rate to the left axis. And we note here that there's a disadvantage because we don't have a legend. Now, at this point, we have to sort of make an apology, because we're going to show you how to add a legend to a plot like this, and it is not straightforward at all. So if you're ever going to do that, you're going to want to have this example. So let's open up a file that's called twin axes with legend. And here is our code. The code at the front end looks somewhat similar, with the exception that with our plot commands for both the twin X and one, we assign the plot itself to as an object to a name, which is called curve 1, and for the second one, curve 2. And then down here, we have a series of statements that allow us to plot the legend on the plot for both curves. and this is required. It shows us combining the two objects into an object called curves, starting an empty array with labels, and then filling that array with labels for the two curves, with the get label, and then plotting the legend for the curves with labels here, and we're giving a location of lower right down here. So if we do that and run it, you'll see that for all that effort, we now get a little legend down here in the lower right. And you might say as you look at that, well, I'm not going to remember how to do that, and that's fine. That's why you have examples like this that you can go back and look at. So let us take a look at that. And here on the bigger slide, it shows the addition of the legend, which is really needed here, and makes a comment that sort of apologizes for the fact that it is a little bit complicated in doing that. All right. So we're sort of introducing features in Python as we go along. All right. Now, the next thing we're going to move to is where you want a figure window with more than one plot as separate plots within the window. And you may have done this before in MATLAB, and we're now going to show you how to do it and how to customize it a bit with Python. All right. So once again, we're going to depend on code that is somewhat longer, and I'm not going to take the time to type the code in. So we're going to be looking for a file here called Figure Windows Example Starter. So let's see if we've got that. Here it is. And now we're introducing some new concepts. First is that we've got a PLT figure, which is what creates our plot window, and we assign that to an object name called fig. You could pick any name you want. And then we define an axis object within that window, and we do it with the add subplot function, and we use a code 121. And what we mean by that is the first one is one row, and then two is two columns, and then one is the first plot of the two plots defined. So we're defining we're defining essentially a plot window with two plots side by side, and the final one here indicates the first plot. And then what we're doing is up here, we've just created some data to plot. So they include going from 0 to pi with 100 points, and then computing arrays of the sine and cosine function. Fairly simple there. And then here in the first plot, we plot two lines, all right, with the sine and cosine function. First one with solid line, second one with a dashed line, and we give it a title. We set the Y labels, the X labels, and a grid, so forth and so on, create a legend. And in doing so, we assign all of these to the given axis that we defined here. Now you'll notice when we do that, instead of just using X label, we have to use set underscore for each of these. That's just the way it is. And then we defined a second axis, which is again our 1 by 2, but the second plot. And here we create a plot of Y2 versus Y1. In other words, the cosine versus the sine. And we do that with our typical commands. So that when we run this, we now get two plots. And the first one is the plots of our two functions, sine and cosine. And the second one turns out to be a semicircle, where we're plotting one against the other. And let's take a closer look at it on the slide here to see what we've got. There's your code that we went through. And the description here to the right is put there to help you understand the code, which we just discussed. And it notes at the bottom the set underscore part of these commands that is now required. And then there are our plots. And what we notice in looking at this is that it hasn't done a very good job of spacing the plots so that they don't crowd or overlap each other. All right. So we want to fix that. All right. And so the way that we can do that is by coming back to our code. All right. And then add a statement. I think we can put it most anywhere, but we'll find out. Fig.subplots underscore adjust. And then we put W space, which is width space, equals 0.5. So we're forcing it to put some space between that. And it didn't like something here. So let's see what it didn't like. Space equals 0.5. Should be okay. Oh, I didn't have an equals, sorry. Won't be happy. Now if I run that, you'll see immediately how it separated the plots, okay? And we look at this, and let me come back to the slide so that you can see it a little better. And you say, okay, we like that, but if I had my preferences, what I would do is I want to spread these plots out a little bit horizontally in a wider window so they're not so rectangular, narrow upward, all right? So there is a way to do that too. So let's come back to our code, and with our plot figure up here, what we're going to do is in the arguments, we're going to put in a fig size, all right, equals, and then in parentheses, we're going to give in sort of an aspect ratio of 8:3, which is going to be more oblong and should provide a little more room for the plot. So let's see how that goes. And there you go. You see, we have created more horizontal space, and our plots look more square and less vertically rectangular. And so we'll come back and illustrate that on our slide as to what we modified there by changing the aspect ratio. All right. And so that we have. And so now to finish up this segment, what we're going to do is we're going to illustrate some examples of how to produce some more specialized plots that you might run into the need to make, maybe not as frequent as standard engineering graphs, but we'll take a look at examples of that. Okay, so I'm not going to save this, and I'm going to go and I'm going to open a file that's called concentration histogram. Okay, so you can see now we're getting a little bit longer code. So I'm going to walk us down through the code, and then we're going to see what it produces. The purpose of this is now to take a sample of data, compute some sample statistics, and then create a histogram or a frequency diagram of the data. And so first thing we do here is we load a series of values that happen to be one value per line or record, so we don't have to worry about delimiters or unpack or anything like that. We can just load it into a variable called concentration. Let me empty my variable explorer here so we've got this ready for that. And so we've got that. And then starting with the NumPy module, I just make a few standard statistical calculations. The mean is for the sample mean or average. STD is for the sample standard deviation, the maximum value, the min value, and I use not an NP function, but a standard Python function called len for length. It would be length in MATLAB to determine how many data I have. And then I just use my standard print statements that you've learned by now, and a couple of them with specific formatting to provide some sample statistics for the data. And then I get down here and I want to use some functions in order to calculate the frequencies and plot a histogram. So the function I'm using in the NumPy library is called histogram. Here it gives you some help on it, and you can always go down and it will provide more help over here and give you more details on how to use it and give you examples, etc. But essentially what I'm saying here is the CONC array, all right? And then the number of bins or intervals is 9. And then the range is 16 to 18.25 for the range of the data. And then I'm going to print out what these edges are, which are the interfaces between the bins. And then I'll print out the histogram values, which are the counts or the frequencies within each bin. So we'll print that out. We've got those data. Now we're going to come down here and we're going to make a plot. So we calculate the width of the bins. We've got n here as the length of the histogram itself, the histogram values. And then we put in a little loop here to calculate the centers of the bins, not the edges. Up here we've got the edges, and this makes use of arrays and makes use of a for loop, and I'm going to defer any details on that because it's coming in the next section of the workshop here when we get into program structure. And then finally down here we make a bar chart, and using the bin centers, the counts, specifying the width, a color, and an edge color, all right? Internal color white, edge color black, and then we do a grid. But here we notice we put in an argument axis and equals y, which means that we only want the grid horizontally and not vertically. And then we do x-ticks as we did before with the arange function, except here we rotate them minus 90 degrees, and that's because we need room for them. And then we put in titles. So as I run this, what I see here is my results in terms of average standard deviation about 0.4, max 18.2, and min 16.1. 197 data. This shows my bin edges, all right, 16 to 18.25. And this shows the counts within the bins, 3, 10, etc. And then if I look at my plot, I have my plot of the histogram, and it looks very symmetric, similar to a normal distribution, perhaps a little peaked in the middle. And that is an illustration of creating a histogram. So let's go back to the slides. And there's that lengthy code on the left. And then we put in some comments which are similar to what I've just discussed with you as we go down through and look at the code. And like for the for loop, we say more on that later, so you have to stick around for that, all right? And you will notice then when we look at the plot why we rotated the labels here minus 90 degrees. because it was going to get crowded to try to put them horizontally, all right, without making the font quite a bit smaller. So that's our histogram. You can see the horizontal grid lines, but not vertical. We don't need those. And the sample statistics over here. And then what we used in order to determine how many bins to use. And there are a couple different rules for that. One is more conservative than the other. It says it'd be appropriate to use somewhere between 8 and 14, so we used 9. All right, so that's your example of the histogram. So we're going to move on to a couple of other examples now that you may find useful. So let's come back over. Let's close this guy out, and let's open one called wind power. And this is to create something, it's a specialized bar chart, which is called a Pareto chart. And here we've got a list of countries, text names for countries. And then we have the amount of power that they are generating using wind turbines. And it's given in gigawatts, all right? So if I wanted to, I could put out here a comment, GW. And then we do a bar chart of country GW with an edge color K and a face color G for green. We rotate our X-ticks minus 90 again and do only a Y-axis grids and put in a title, all right? So if I do that and run that, this is the kind of plot that we generate. And with the Pareto chart, what you're looking at is it's a trend from max down to min. Sometimes these are done, bars are done horizontally, but here, excuse me, we have shown how to do them vertically. And you can see the need for the rotated labels. Looking at that on our slide, this is what we see. So you have an example of how to do a bar chart where your categories on the x-axis are actually text labels, and then you have numerical values on the left. All right, it's not frequencies, but it's an actual quantitative value in here, gigawatts. All right, so that's an example of doing a different type of bar chart. Again, using the BAR function in Matplotlib pyplot. Okay? So the next example we're going to look at is going to be using logarithmic scales instead of regular scales. So let's pop back over to our Spider editor and let's look for a vapor pressure H2O starter. Should be way down at the bottom somewhere here. Whoops, I didn't want that. Let's get rid of that. Here we go. So you can see why I didn't want to type in this code during the workshop, because it would be pretty lengthy and I might make mistakes. So what we are doing here is we've got a set of data of vapor pressure of water. It's essentially the steam tables for saturated steam. And we've got a range of temperatures, and we're showing a couple tricks here. We got a range of temperature which goes from 0 to 220 in steps of 10, but you'll remember that it always leaves out that last item with the arange function. By the way, the linspace function includes the final item. And so it's going to generate an array of 0 to 210. And then we actually have an extra data item at 212 Fahrenheit, which is 100 Celsius, and that's the boiling point at 1 atmosphere. So what we do is we add that value to the TF array just by specifying it. So we expand the TF array by one value using the append method. All right? It's the first time you've seen that here. And then given all those Fahrenheit temperatures, we convert them over to Celsius temperatures. And then we create vapor pressures by just entering from data, from tables, what are the values. All right? And this is values in kPa, which you can probably tell by looking at the last one, 101.3. And then we have a way of predicting this, which is called the Antoine equation, which you're familiar with. And here we calculate the predicted vapor pressures from the Antoine equation. And you'll notice that our TC here is an array. And so this is evaluated as an array function and produces an array of pressures predicted. And the comment I'll make here is you may note that if you're going to do something like this in MATLAB, you have to get involved with using dots with your operators in order to do this, like, you know, dot caret and dot slash for that. You do not have to do that with Python, which is convenient. Of course, it gets less convenient in Python when you have to do calculations with matrices and vectors. And then what we want to do here is we want to create a plot, all right? And I'm going to change these values here to just a standard plot, like so. And so we're plotting two things here. We're going to watch them. We're plotting the actual data, all right? And in this case, the line that we're using is invisible. It's white. But the marker is a square with a black edge and a white center. And we're giving a legend for this steam tables, all right? These are the data from the steam tables. And then here, for the Antoine equation, we're plotting a line, but no markers because this is an analytical function. We're giving it a given line width, and we're adding a label for our legend, all right? So if we run that, this is what we see, all right? So let's come back and take a look at this on the slide. And there it is. And you can see that's a very nice plot, and it shows that the Antoine equation does a pretty good job of representing the actual steam table data. It's not perfect, but it's pretty good. And the only other problem that we've got here is that the ratio of this vapor pressure, 101, to this one is about 800 to 1. So down here, where variations are like 1/800th of variations up here, and it doesn't show very well on a plot because it flattens out so much down here. So that gives us the idea that if we used a logarithmic scale here, it might show the variations down here better, at least on the plot. So that's when we come back and we change this, and this is very similar to MATLAB, where we put in semi-log y. In other words, create a log axis for the y-axis, the log scale for the y-axis for both curves. Spell that right. Semi-log y, all right? And then we're not changing the numbers, we're changing the plot scale. So if we run that now, we get a plot which shows the variations, and it's interesting, and I'm going to come over to the slide so that you can see it a little more clearly. And what it shows us here is that there is a bit of a bias for the Antoine equation when we get down to low temperatures, okay, in Celsius. When we get down to low temperatures, that a bit of a bias, and the Antoine equation is predicting a bit high from the actual data, which are considered to be accurate. And so one way of thinking of this is maybe this is why in many cases they actually use the tables here and they don't use the Antoine equation. But at the same time, if we go back to our previous slide, you really couldn't see that variation with the scale here, but you can see it in this plot. And there are alternate functions we point out, which are like MATLAB, which are semi-log x, where you're making the log scale on the x-axis, or log-log, where you're using two log scales, okay? All right, well, the last thing that we're going to deal with here is to look at contour and surface plots, and that will finish this segment of the workshop. So hang in there. Let's see where this goes. We're going to start by looking at a contour plot, which is based on an analytical function, and that's called contour analytical. So let's go find it. Contour analytical, there it is. All right. And this turns out to be very similar to MATLAB as a point of reference. Here we are creating NumPy arrays of 50 points each, and they are X and Y, and they go from -2 to +2. And then we create a mesh grid using the X and the Y. And one way of thinking about that is to consider the X along the X-axis, the Y along the Y-axis, and we're creating essentially X and Y two-dimensional arrays that give us the coordinates at each point on that flat space, which is outlined by X and Y. And then for each one of those coordinate points, which are now two-dimensional arrays, we calculate a Z value, which you consider like an elevation above the X and Y plane. And here it turns out that it is just what's called a quadratic response function, where it includes a term in X, a term in Y, X squared, Y squared, and a bilinear term in X times Y. And then we create a figure, and then we create a contour plot. And again, here you can see what these arguments are, and if you want, you can generate the help up here to see more detail. And then the only thing that is different in here from what we've seen before, X, Y, and Z, or Z, is that we specify which contours in values of Z we would like to have labeled, and the colors, and then we put in a C label for the plot, and that is the one that labels the contours. So if we run that, let's look at our plots. This is what we get, and it's pretty nicely done for us. And it provides our scales -2 to +2, and you'll notice that it does our intervals as we wanted, 75, 80, 85, and 88 as specified here. So coming back to our slide, there is our code. And one thing we note here is that the X and the Y are one-dimensional arrays with 50 elements. The reason you have 50 is because you use linspace without a third number like 100. So the default is 50. And then the X array, cap X, is 50 by 50, as is the Y, and the Z is 50 by 50, and those are the arguments to the contour plot, and this is what you get when you run the script, all right? Now, sometimes we want to make contour plots which, instead of being so quantitative here, are actually have the bands colored to give us more of a qualitative idea on the shape of the contours. So let me show you how we can go about doing that, all right? And so let us go back to our code and let us and again, this is somewhat similar to MATLAB. Here, instead of contour, we use the contour F standing for filled. And then we have a slightly different set of intervals here. We add a 92. And then we specify colors which are between each of these pairs, which is blue, green, cyan, and magenta, and the rest of the commands are the same. And when we run that, this is what we get, all right? We don't have the labels anymore, or they may be hiding in there, I guess. Yeah. They're a little hard to see. We might not prefer to have those. Let me comment that out for a moment and see what happens. Okay, now they don't show up. So this is what we have there, all right? And so let's come back to our slides and see that that is what we have. And you'll see that that C label function is missing here. And this is the plot that we get, and shows you how to use contour F, all right? Okay, so we're going to show you a couple more variations on this. One is a different type of contour plot, and then finally we'll show you surface plots, all right? And that will finish up this segment, and we'll all be ready for a little break, I think. So here we go. Let's come back over. Let's close this out and close this out and open a file called NaCl density. Contour plot. Okay, so let's take a look at what we have here. It's a little different, because now what we have is, for salt solutions, we have one variable which is the weight percent of the solution from 1 to 26, and another one which is the temperature of the solution from 0 to 100, all right? And then we create our mesh grid with these two one-dimensional arrays. And then what we do is we load from a data file the actual density values instead of having to enter them, because it's a bit tedious, all right? And we have them in a text file instead. We'll show that to you in a moment. So we load those, and then we create a figure. We do a contour plot, all right? The same way we did before. So let's look at the result, and then we'll go back and look at the slide for a few more details. So there's the result that we get, and it gives us some nice labeled contours in terms of density, gives us an idea of the dependence of the density on concentration this way and on temperature this way, all right? So it gives you a good feel for that. And then let's come back to our slide and take a look at that. First, on the upper right-hand corner here is actually just some data that we have on a spreadsheet, on an Excel spreadsheet, taken from Perry's handbook. And these are the data that we have, all right? And then we have transferred these data into a comma delimited file, all right, from Excel, a CSV file. And these are just the density data, all right? And they are exactly according to the table here. And then we have, after that, actually more entries here than there are here, I believe. And then these are what are read in for the temperature 0, 10, 25, 40, 60, 80, 100. So this table here doesn't show the 60, 80, 100, but this particular comma delimited file contains those items so that you have 7 columns instead of just 4 columns up here. So that's how we've gone about creating that contour plot. Now, let's finish this up by considering surface plots, all right? So let's come back. And again, this is somewhat similar to what you see in MATLAB if you've created these plots in MATLAB before. So let us go to what we call surface mesh analytical. Okay, now we've got a couple tricky things happening here. But the first is that in order to do this, apart from pyplot, we need a module called mplot3d from the MPL Toolkits module. And then from that, we're importing something called axes 3D, three-dimensional axes. And you'll notice here, out here, it gives us a warning that it's imported, but it's unused. And all that I can tell you is there may be fancy ways to get around that warning. I've looked into them, but they're not worth our time here. And the warning is essentially a lie, all right? Everything works fine. You just have to ignore the warning here. And I apologize for that, but that's the way it is. And so here we've got the same type of thing where we're creating our function based on a mesh grid of x and y from -2 to 2. And then we come down and we are somewhat different because we create a figure object using the PLT figure function. And then we name an axis object, and we add a subplot 1, 1, 1. Now what that means is that you just have one plot, one row, one column, but we have to include the fact that we're using a projection here, which is 3D. And then here we're using the wireframe function to plot z versus x and y, and we use 2 arguments called r stride and c stride, and I will describe those in a minute in terms of what happens when you change them. And then we have grid, we have some x ticks, y ticks, z lim, limits in the z direction, z ticks, and then we plot that, and then we have an angle of view which is called 35 degrees. So let us take a look first at the result that we get, and then I'm going to experiment a little bit. So there is the mesh diagram with the x, the y, and then the z values. And we're looking down at it at that 35 degree angle. So if I come back here And let's say I change this R stride to 10, whoops, 10 and 10, and let's run it again. And you'll see that it's not as dense a mesh. And then if I were to put it down to 3 and 3, it is a much denser mesh. So that's something where pretty much you'd arrived at the value of 5 for the stride, what's called the stride. And if you use a stride, if you don't include these, you essentially just get a black surface, which is not very instructive for a mesh. So that's that. Now, if I come down here and I were to change this to 20, what's going to happen there? And you can see that we changed the angle at which we're looking at the surface. So that's what that is. Let's look at the slide on that. And we make a note that the warning here is false. You do need this novel. And the stride arguments indicate the data count intervals for the mesh lines. So that's what we give you there. And then the last example that we're going to illustrate is how, instead of having a mesh plot, how you can have a shaded surface plot, all right, which is the final thing. So let's open a file to illustrate that, and that's going to be Surface Analytical. And everything looks somewhat similar, except we get down here and we have plot surface instead of plot wireframe. And as we look at that, we see that we got X, Y, and Z, and then we use a CMap cm.blue, and this is up here, all right? And you'll notice that we do not require the Axes 3D one here. We just require from Matplotlib the CM, all right, submodule. So we've got CM color map.blue, and then the rest of this is very much the same. And so when we run this, whoops, we don't have that right yet, do we? We want CM gray, I think. Let's try that. There it is. Okay, so you get a shaded surface, and if you want a different aspect of it, you could take it down to 20 degrees and look at it a little bit differently and get an idea in terms of the shape, all right? So this, coming back to our slides, is going to show you how to convert it over to a shaded surface, all right, instead of just a mesh, all right, surface plot. And this is the end of our exploration of the different kind of plots that you can create with Matplotlib. There's an extensive amount of information in the help file for Matplotlib, but we've tried to give you an overview of the plots that you might encounter most frequently in engineering and scientific work. So from here, we're going to move on and we're going to start looking at program structure in Python, and then we'll also talk about how to deal with matrix and vector calculations instead of just array calculations. So let's take a break here and we'll continue a little bit later on. You probably need a break too.